right, assuming everybody can see my presentation screen. If not, speak up. But so I'm going to talk to you about some challenges and approaches that we utilize to develop a whole system hospital model. And this project was very interesting and kind of fun to do from a simulation perspective. So I'm happy to share it with you. It does have a different flavor than the other two presentations that you've seen, but hopefully you'll still find it valuable. So one thing I do want to note, this is a partnership with UC Health that we developed this project. Any data you see in here has been masked. So know that you're not seeing UC Health data. Don't want to violate any HIPAA laws or any privacy for that organization. So a little bit of background on this project. I know Glenn spoke about this earlier, but this was a student-based project that was supporting the partnership with UC Health and our Center for Business Analytics. So the team was composed of two MS Business Analytics students, a project manager, a project advisor / mentor, that was me, a team leader from UC Health, and then an advisory team from UC Health. So kind of under the boundaries of this project, we were kind of time bound in that it needed to be completed in one academic semester. So we were looking at a 15-week timeline. The project team, if you want to put names by this, the project manager was William Bressler, who's on this call and part of the Center for Business Analytics. We had two students, Alexandria Bianco and Wakas Tanvir, excellent MS Business Analytics students who did, worked alongside with me on this project, and then myself. From UC Health perspective, I put the names and titles here because I want you to show kind of the emphasis that UC Health put on this in dedicating resources. Our team lead was an assistant vice president, Tyler French. We had the associate chief medical officer, Stuart Wright, with us, a manager of capacity management, Nicole Plaka, and then the director of emergency management, Maria Friday, working with us throughout the project. So very good support from their perspective. Just a little bit of background on UC Health. We're focusing in on the University of Cincinnati Medical Center. So this is a very large hospital system, and it has more than 500 inpatient beds. And it's very academically driven hospital. It's got a wide range of board certified physicians and specialties in medical and surgical areas. So it's a very complex institution as you look at healthcare. And what we wanted to do, what UC wanted to do as we entered into this project was better understand how they could allocate physical resources with the idea that they wanted to make some modifications to a surgical specialty area. So our project goals as we set out were to build a model that accurately reflects the hospital's current patient flow process. We wanted to be able to utilize the model to identify bottlenecks and some system limitations, and then understand from a system level consequences of hospital decisions or changes. Now, in a 15-week project, you're probably thinking, wow, if they accomplished all of that in 15 weeks, they're pretty amazing. We would be, but we didn't get all of these done. What we did is we're actually able to set up a model that, as we iterate through, that will permit us to do those types of things. So we're in step one of a multi-step activity here. But these were the goals, very important for us to know as we started out. So as I talk through this particular project today, what I'm going to first talk about is kind of our modeling approach, the data analysis that we did, and how we utilized iterative model development to execute this project. I'll review our model design in a little bit more detail than you've seen today, talk about model applications, and then how we can use and improve the model. So kind of backing up, not all of you have spent, more than a decade working in the healthcare environment, but the healthcare environment is a very complex system. If you look kind of at a brief definition of a complex system, the system is dynamic, behaving differently according to its initial conditions and feedback. And as we kind of look at the hospital system, it is very, very complex. We have nonlinear cues in that somebody that comes in with a higher priority, a higher acuity, jumps the queue and takes away, it gets first priority. So we've got some nonlinear cues. We have a lot of random variation and a lot of uncertainty in the environment. Nobody schedules a heart attack. Nobody schedules a car accident. And as those patients come into our hospital, they're going to need different things. They're going to require different times and different elements. And so we've got a lot of uncertainty to deal with. While we still have fixed capacity and high occupancy in our systems, we don't have a lot of spare resources sitting around the healthcare system because it's very expensive, as you know. So, we've got that fixed capacity, high demand, a lot of variation. So we've got some costs of waiting, which are not necessarily just monetary, but in the outcomes of patients. The longer you wait for care, it's been proven that the worse off you're going to be. And then we also have what we call flow failures. So as we were embarking on trying to meet our project goals, we really scoped this project to the inpatient units in the hospital. So when you go into a hospital and you stay overnight in a bed, that would be considered inpatient. So we scoped it there, and we excluded things like surgical operations and emergency services and other activities that go on in the hospital. So that was our scope. And then what we wanted to understand was when we had like failures and being able to meet the demands of what patients needed. So this is our complex environment that we're dealing with, and we had to try to identify how we could handle that. So as we looked at this, we looked, kind of at our modeling approach. So if you think about this, it's really too complex for mathematical models without utilizing a lot of assumptions, kind of assuming away a lot of things. Queuing models might work, but as we start to look at the whole system, they quickly get too complex. So we decided that we would use discrete event simulation that would allow us to vary the demand, vary the patient paths, vary the uncertainty in patient needs, really kind of capture the system. Excuse me. And we utilized Arena software from Rockwell International for our model development. So we developed a discrete event simulation model that would be used to model our hospital. So, excuse me a second. So some of you may be very familiar with simulation modeling and others of you may not. So let me just take a brief moment to talk about what simulation modeling is. So a simulation model is a mathematical model of a real-world system that we do on a computer. And we can use the output of that to describe or predict behavior of the real system. And this is terrific to use in a healthcare environment. We're going to try it on a computer before we try it on a sick patient or with a lot of very expensive personnel. So we can try out multiple things on a simulation model, understand what our best path would be using the output of that, and then go execute that in the system. It saves time, effort, money, and could save people's lives. So developing simulation models is a terrific way to kind of explore improvements in your hospital environment. So as we started down this project, you can imagine it had to be data driven. And UC Health provided us with a very nice data file that included 2 years of data. And this data was extracted from their Epic system, and it included approximately 50 columns of data. And this is just a quick sample of the data that we might have pulled out from that data file. I got a tickle in my throat at the wrong time. But so you can see here, we've got like a patient identifier to talk about which patient this was. We have an encounter ID, which identifies like when they first entered the hospital, their admission type. We've got an arrival time and a departure time. But you can see this particular patient had an encounter ID of 99999, and they came on October 1st. They were first put in the medical ICU, the MICU, and they were there for about just over a day. And then they transferred to kind of what we call a step down unit, 7 Northwest. They stayed there for 3.125 days. And on the 5th, they got worse and they had to go back up to that higher level of care in the NICU. So this patient stayed 9.29 days in the hospital, and they were in 2 different units while they were there. Now, as we look at this, this was one patient. And what we found in our range of data over 2 years was that we had about 60,000 patient encounters, so patients being there. And that could be overwhelming to think about analyzing unique paths for each of those patients. So what we started to do was start to understand the data. And at a high level, what we discovered was, 77% of the patients that we found in our file were discharged after what we called the first stop, or their first unit. And, then if we kind of go on cumulatively, what we then found is like by the time they may have gone into 4 units, 99% of the patients have been discharged. So they gave us a good slant that says, maybe I don't need to model to all 13 layers that a patient might go through. Maybe I can start to focus on, the top majority and get a good analysis of the system. So that was very insightful for us as a first step in understanding this data. We then explored many, many other elements, and these are just some of the outputs that we used here. We explored these using Excel. We did some data analysis in R, and looked at different things like, where were they going next? What department? What percentage were discharged or transferred from different places? What was the admission volumes at different areas? How long did they stay? So we did a lot of different data analysis, which kind of allowed us to really understand the system better. And then identify, here's some common groupings that we might be able to use for this model. We discovered we had 7 different admission types, and coming from the emergency room was dominant. We had department groups. We had 5 categories there. Med surg and critical care were very dominant there. We had 27 departments. We had 7 levels of care, and patients moved in between those, and 42 services, 28 distinct units, and a lot of options for deciding how to model this. So we worked very closely with our UC Health partners, and what we determined was, given the goals of their project and to look at maybe making some modifications to a specific surgical area, we decided to model this by service. And that would be the predominant focus that we would have as we were modeling our simulation or developing our simulation. So then we started to, try to understand things a little better. And what we did, we called like our stop analysis. So here's an example of what we found as we looked at the patient flow, or how the patient moved through the inpatient units. They may have started out in, say, unit A. And then what we discovered is like, they went to maybe unit 2 or unit 11, unit 21, a wide variety of units, up to 28 of them, where we could see where they went. And each of them had a different probability based on this historic data of where they would go next, and varying lengths of stay. So as we looked at this, this was unit A. They, in this example, about 16.5% of the patients would flow from unit A to unit 2. Then we took unit 2 and said, okay, if they went from unit A, they went into unit 2, where do they go next? And then we found that unit 21 was prevalent, unit 22, actually, maybe most of them were discharged from this unit, and things like that. So as we started to explore this, you could imagine then we would have to go to unit 21. Where did they go here? Unit 22. So we quickly got a very wide web of where patients would go, and deciding how and when and where to kind of cut that off was kind of trial and error as we worked through the model. So kind of understanding all of those, this was like how we developed our conceptual design. So how are we going to design this model? And I'm skipping a bunch of data analytic steps as I jump into our conceptual design here, because we're limited on time. But we define arrival patterns by service for our model. So we're going to describe those by service. And we're also going to define the patient flow by service. So if they came in and say the medical service, we were going to model their arrival patterns and then how they flowed through those various units through what we called 3 stops. So their first unit, their second unit, and their third unit. And we would say, okay, if you went to this first unit, where did you go next? What probability were there? And then the second unit, third unit. So we were doing by service, 3 stops. And then we developed discrete probability distributions of the placements to the 98th percent level. So we didn't include the bottom 2% of placements. Sometimes, usually those were had an N of less than 10 over a 2-year time period. And we kind of considered those outliers. We decided not to differentiate length of stay by service, but rather we had that by unit and by stop. So one thing we discovered is that patients that at their first stop actually usually had a shorter length of stay than if they had a second stop or a third stop. So we had done some equality of means testing for each of the units and determined that we needed to differentiate those by whether they were at the first stop in the process, the second or third. And then from a scope perspective, we were modeling 22 of the 28 units. There were about 6 separate units that were excluded from this analysis for the hospital. So we had 22. And then one of probably the biggest things that helped us in this is that we decided, as we were trying to model, 22 units and about 20 service groupings, we needed to be able to model those very easily and create distributions of length of stay and where patients were flowing. So we decided to use data arrays for consistency, flexibility, and repeatability. And each unit was assigned a number, each service was assigned a number, and then throughout the model, we just referenced that number or that combination of unit number and service number to help us achieve our goal. Our arrival patterns were Poisson distributed by service or service group. We did this by day of the week and by hour of the day, because you can imagine Saturdays and Sundays, the arrival rates were lower. You get fewer arrivals at 2 in the morning than you do at 2 in the afternoon. So we did this again by day of the week, by hour of the day, and by service. And this provided us very realistic flow patterns. The only negative to this was that it excluded seasonality in the data. And that may be something we want to come back and try to build in at least to some of the services at some point, but we currently excluded that from the model to get an understanding of some common outputs that we could use. This is just a quick snapshot, you don't have to read it, to show you kind of what some of our distributions look like. So we used discrete probability distributions to determine where patients would flow, like which next stop they were. So you can see here, we had them by stop and by unit, by stop and by unit. And it determined randomly where a patient would flow based on the historic values. So we created sets of these distributions for each service. Was quite time consuming, but one of the things that we did, we actually utilized Excel to help us build this, and adding a few columns and summary values into our data file, we were able to have Excel fit these distributions for us, and we used filtering capability to do them for each individual service. Our length of stay, so we segmented our data by unit and stop, I mentioned that. We utilized a tool from Arena the software that's called Input Analyzer. And this is a really handy tool in that it will, if you give it some data, it will fit a best distribution for you. So this example here I've got was exponential distribution. And, we could see we had over 1,000 data points that went in there. And so we developed unique distributions for each unit at each stop, a total of 66 unique length of stay distributions, which took quite a while to compile and develop. But we did use this tool there. From a process perspective, from a process flow, as we were thinking about this, patients were created on an hourly basis by day of the week using a Poisson distribution. And what we would do is we would create our patient, and then we would assign an attribute, we call it, for our patient that said where they were going. Are they going to unit 12? Are they going to unit 13? Are they going to unit 22? Where are they going? And then we would route them to the appropriate service so that we could pull in the distinct flow patterns. And then once they got to each service, we followed this conceptual view process flow. So after the admission, we pick the unit. So what unit were they assigned? They were assigned unit 1. We come up, secure a bed in unit 1 for that patient. The patient would stay in that unit for their randomly selected length of stay. We would then use our discrete probability distributions to determine the next stop. We would assign a bed in the next unit and then release the bed in the current unit, and then circle back and go get our next unit. One thing that we had to make sure that we build in here, we didn't initially, was this assignment focus, because generally if you are queuing for something, you go wait in line. But if I've got a patient in an ICU that's waiting for 7 Northwest, I'm not going to go send them to wait in the hall if there's not a bed available in 7 Northwest. They're going to stay in that ICU bed until 7 Northwest is available. So we needed to make sure we assigned them and kind of reserved them a spot here before we move them out of their current unit. And that, that would have been a delay. So we just process here and then again until the patient's ready to discharge. This is actually a snapshot from our ARENA model that you can kind of take a look at. We secure our admission bed outside of any inpatient unit. So one of the things that we needed to do was, as a patient arrives, we needed to put them in what we called a hold bed. That would have been the equivalent of waiting in the emergency department or in the PACU if you had surgery for your bed to be available. So we put them in a hold bed until a bed in the unit that they needed was available. So we held them there, and then we determined where they were going to go. We captured their start time so that we could create some metrics. We secured a bed in the unit they needed, released the current bed, and then we capture measures. They stay as long as they need to. We increment the number of stops. And then we identify the next unit for the patient to go to. One thing I will say, so we modeled this for medicine, for cardiology, for ENT, for all of the different services that we had. And one thing that would have been nice that is not included in ARENA is dimensionality. So we had, as I showed you in the stop discrete probability distributions, we had kind of a two-way distribution where we were saying what stop was it, what unit was it. Had we been able to have like three-way dimensionality in our model, we could have actually just had one model and not a separate unique model for medicine and cardiology and stuff. We really were just replicating the exact template across models. And had we had a three-dimensional opportunity, we actually could have just had a very simple model when it came down to looking at it. Here's some example of output that generally comes from ARENA if you're doing discrete event simulation there. We get a lot of data related to like entities, and it will generate an average, a half width, a min and max average, and then a min and max value for you from your data. and it'll generate common statistics for process queues, resource utilization, time, volume, and things like that. So we were able to get a lot of output automatically from Arena, but there were other measures that we had to set up the model to generate. And I know I'm short on time, but here's some of the models we did. We did a validation by service. So we looked at things like, we had 16 different service groupings we focused in on. We looked at patients. Was our model producing that? The length of stay, how long were they staying? Was our model matching what we saw in historic data? Flow delays, that's when, in the example I talked about where I had a patient in an ICU bed waiting for a bed in 7 Northwest, there wasn't one available. They stayed in that ICU longer than they really needed to. So we would have called that a delay and captured that wait time for a bed to show up there. We also looked at stops. How many stops were patients making on average, and were we good there? We also validated things by unit. We looked at utilization of the various units. We looked at waiting and delays by unit. We looked at it by service. We also looked at it by unit. And then we looked at inflow delays. That would be those delays where patients had to wait to come into our unit, or when patients had to wait to come out of our unit. So we looked at those delays. So finally, kind of gave you a picture of kind of our whole model. How did we develop it? Well, we used an iterative development. Once we developed that conceptual process, we decided to develop it for one unit. We started at one unit, high admission, high volume unit, and we modeled that out. And we discovered as the flow, as we developed our discrete flow distributions, that it flowed to 12 units. And then we started to measure and see how it did. And we were able to confirm flow patterns very well with that initial assessment. We weren't able to confirm length of stay and utilization because our system wasn't busy enough. Then we expanded the model. So we did a single service. So all medical patients, or all cardiology patients, or all ENT patients, we did a single service and all the units there. Again, we were confirming flow patterns, confirming arrival patterns, but we weren't able to get to length of stay and utilization. We then expanded it to include 5 services. Again, doing better, we're getting a better picture of what the hospital looks like. And then finally, we expanded it to include all services. And this is where kind of our wheels fell off, and we were like, oh no, this is not good, because it didn't validate well. And if we looked, we had really long lengths of stay because this was due to excessive waiting. So patients were waiting a really long time to get into maybe 7 Northwest. I picked on that unit during this presentation. So excessive waiting. And what we were missing was the manual interventions that occur in a hospital. So in a hospital, we had Nicole Plaka, who was a manager in the capacity management area. If she saw that a certain unit was really busy and we had a lot of demand for that unit, she would place some patients on an alternate unit. And then she would kind of peel away some of the demand. So they weren't waiting, and we were taking available capacity in another unit and utilizing it. Our model didn't handle that. So we needed to incorporate that decision-making that was being done to manage the entire system into our model. And this really improved our validation. So conceptually, we said, okay, what do we do? If a patient waited for their next bed longer than a set delay threshold, and that was about a day based on input and conversations with UC Health, we routed them to an alternate unit. And this was based on historic overflow placement, and again, partnering with UC Health to get this information. Once the patient was assigned to an alternate unit, they were routed back into their normal service flow, and they finished their stay at the hospital. Actually was implemented using this. So we created a daemon that looked every 10 minutes and said, okay, is anybody waiting more than a day for placement in a certain unit? And if they did, then we used called a search and remove. So we would search all waiting queues, and then remove patients that met a certain criteria. So they had to have been waiting longer than our delay threshold, and the place that they were supposed to go had to have available beds. If that was true, we pulled them out of that queue and put them in the alternate unit. If that wasn't true, maybe they've been waiting more than the day, but there were no spare beds, they stayed in that queue until either a bed freed up that they needed or a bed freed up in their alternate unit. So that really helped our process and helped us with validation. Now, we're not completely validated. Again, we're going to iterate through this hopefully in another student project soon. But we were able to validate 2 output statistics at 100%. Our patient volume was great, and our average number of patient transfers or stops validated very well. 3 output statistics were partially validated. Our utilization, 56% of the services were validated. Our average flow delays, 13% of those were validated. And when we're saying validated, we were using kind of a plus or minus 5%. So it's a really tight window to be considered validated. Maybe we should have relaxed that, but 13% of our services were validated from a flow delay perspective, but all of them were within 0.2 days of the historical data. So we weren't far off if we were off. The average length of stay, 31%, again, we're within plus or minus 5% of the historic average, but all were within 1 day. So we were getting pretty close. Probably we just need to do a few tweaks to some of our models there. Kind of to show you the output, I don't know if any of you have done discrete event simulation before, and hopefully you can see this. This is a very small snapshot of our, what we call our animation of our model, visualizing the system. And hopefully you can kind of see the little people flashing and moving in here. This represents our system. So anytime you see somebody like people like standing above here, these are the number in queue for a particular unit. And again, they weren't able to go to their alternate unit, so they're waiting. And we did things like color coding the different patients visually to represent the service that they were representing, so we could easily see when patients were being placed in an alternate unit, things like that. So visualization is very helpful in communicating how your process and your project is going, and so you can see where the problems occur. It actually helped us to debug some problems that we had in our system, but you know, very helpful and very powerful when you're communicating, especially with doctors. If you can show them, or any managers, you can show them what's going on in a model, they'll be like, oh yeah, that's exactly how it feels. And it really helps in getting buy-in to implementing changes that you may discover in the model. So how can we use this model? Well, a lot of different ways. We can trial different bed configurations. We can look at what happens if we add new units to the hospital. We can evaluate changes to capacity. I'm not sure if any of you have worked in healthcare, but occasionally we have to shut down beds for renovation to keep inpatient beds, you know, current with technology and with improvement. So what happens? What's going to be the fallout of shutting down 4 beds in this unit for renovations? We can run that in the model and find out. We can trial growth in certain areas if maybe we're starting up a new program, evaluate effects of scheduling, maybe in surgery. And we can explore different overflow strategies. These are just some of the things we thought of. Many ways you can use this model once you have it available. Here's just a quick example of how we simulated using the model to assess bed allocation. So you can see what we did is we identified different scenarios, our current state, adding 1 bed through 6 beds, removing 1 bed or 2 bed, and then we identified key measures that we wanted to look at to evaluate what happened. And this visual kind of shows you some of the key measures, what might happen if we, again, add capacity, take away capacity, and really run simulations of each of these different things and provide you with outputs. So you can be better informed at what might happen. Average number of flow failures. If I remove 2 beds, it's going to be at least 50% higher than it currently is. We need to be prepared for that if we need to do some renovations. So it really quantifies things for you. Some of our limitations, our current length of stay includes system delays, and it may actually be inflated. And what do I mean by that is currently our system, it's a very highly utilized system. So there are delays included in there, and we may be baking those into our length of stay distributions in our data. That's something we need to keep in mind. Our length of stay is currently not service or diagnosis specific. That would be an enhancement that we could make on an as needed basis if we found a service that had distinctly different lengths of stay for certain diagnoses. We didn't include seasonality, and actually our data also included data from COVID, and you might be surprised that we kept that COVID data in there, but it was the most recent data that we had. And when we looked at the annual values and annual results, believe it or not, it wasn't that different from the prior year to the year 2020, 2019 and 2020. So we decided to keep that in there. And our overflow modeling that we added to put the wheels back on our bus isn't quite as robust as the current interventions. Obviously, a human can make better decisions than we can build into a model, but it definitely helped us to incorporate that decision making into our solution. So kind of wrapping up. So what were the keys to our success? I mean, we developed this model in 15 weeks, actually less than 15 weeks. Anybody that's worked on any complex large data project, hopefully you're impressed. I was. But how did we do this? Thorough data exploration was key to this. We spent more time in data exploration than we did in model building, making sure we really understood the process. One thing we did was clearly identify similarities and differences between units, between services, between lengths of stay. What's similar that we can combine, what's different that we need to handle. Our recognition of outliers and unexpected behaviors also helped us to be successful. We didn't try to model everything, which was very helpful. And our iterative development process, not trying to do it all at once, kind of starting one unit, one service, multiple services really helped us to learn and make tweaks rather than trying to do it and redo the whole system every time. And our use of arrays to denote service and units was tremendously helpful from a design perspective. It saved us a lot of time and allowed us to generate things, outputs in Excel or R that we could feed directly into our models using kind of array functions. And last, but certainly not least, I probably should have put this first, strong partnership and buy-in from the project team. Great support from UC Health, from the Center for Business Analytics, and having a team that was very focused and working toward the goal was extremely helpful. So I'll wrap up here and just say, any questions, but before I do that, I do want to give a special thanks to Bill Bressler from the center, Alexandria Bianco and Wakas Tanvir for the contributions that they made to this project in this presentation, not excluding UC Health, but they were integral in this, and I don't want to take the credit for all the work. This was a team effort.